Okay, so I've rewritten out the equilibrium reaction that's occurring, and I've highlighted in blue and red the two primary species that are present in the reaction before we add any of our acid or base. Okay, so at the start, before we add any HCl in part B, we have 0.2 molar of HF and 0.25 molar of KF. And usually in rice tables, we like to use molarities. But when we are solving buffer problems, we're actually going to need to convert everything into moles because we need to do a subtraction of moles from one thing to another. And so you're going to have to do the extra step of converting those molarities over to moles. And pro tip, converting molarity to moles, all you have to do is take the molarity times the volume. So you'll notice that looks pretty similar to M1B1 equals M2B2. Okay, so for HF, its initial concentration is going to be 0.2 times the volume of the buffer. So 0.2 times 1.5 is just 0.3 moles. Water, remember water and H3O plus aren't gonna really contribute to anything that's happening. See if I can find a gray pencil. So I'm just gonna gray those out so you recognize that you don't have to worry about them. H3O plus isn't really present. It's present in a really small quantity, but in comparison to the blue and red species, it's not really, there's not hardly any of it, so we can ignore its contribution. So you don't have to worry about anything here or here. Okay, and then we need to find the number of moles of F minus, which we just get from taking the concentration of KF times the volume. So that's just 0.25 times 1.5, and I could do that math this morning. I don't think I can do it anymore, which kind of makes it all the more impressive that I could do it this morning. Good job, brain. Okay. So these, I'm just going to put in parentheses, are all moles. Okay, but then in part B of the problem, we do something crazy, which is adding some strong acid to our buffer. So we're going to take some HCl and we're going to add it to the reaction that's already going on in solution. And so whenever you add HCl, the thing that you're actually adding, it's not just HCl, it's basically H+. So HCl is a strong acid and will immediately dissociate into H+ and Cl-. So we can think of that, it's okay, I think, just to think of that as H+. Okay, so when it produces H+, let's put that in yellow, you look at the reaction that's occurring in solution. So let's bring our attention back to here, and you decide like which one of these species is the H+ going to react with. So it's going to react with the thing that is opposite in charge of itself. Okay, so something positive will react with something negative and vice versa. And so of all these species that are present, the one that's going to react the most and completely is actually F-. So H+ is going to react with H- to do this reaction up top. So H+ plus F- will react completely, 100%, because it's basically the opposite of that first reaction we wrote. It's going to react completely 100% to form HF. Okay, so all the H+ is going to be gone, so that does not affect this column. However much H+ there was is going to react with however much F- there was. So if we know the number of moles of this, we can figure out how much of this F- is going to disappear and how much of this HF is going to be added. Let me see that one more time. If we know how many moles of this we have, then that will directly tell us how much F- disappears and how much HF is added. Okay, so HF, I didn't want to draw that. HF is going to increase and F minus is going to decrease by whatever amount of H plus you added. All right, so we can quickly calculate the amount of H plus that was added just by taking its molarity times its volume. So 0.2 times 0.025 liters is 0.005 moles of H plus. So that number will be the amount by which F minus decreases and HF goes up. So we can take that 0.05 moles and put it in our change column. Another way of thinking about it is that we are adding something to this equilibrium. So we're actually adding a product to this equilibrium. And based on Le Chatelier's principle, if you add something to a side of the equilibrium will shift in such a way as to relieve that tension. So if you add something over here, the equilibrium will shift this direction, producing more HF and reacting away some of your F minus. So I'm going to write down in our change column that we are adding 0.005 moles for HF, and we are subtracting the same amount from F minus. Okay. And then you get to your equilibrium column, which you can just add everything together. And everything is great until you recognize that everything is still in moles. Before we can plug anything into the Henderson-Hasselbalch equation, remember that the numbers from the Henderson-Hasselbalch equation are in brackets, which means that they're in molarity. And so we need to divide each of these by the total volume of solution. Because we added two different solutions together, our volume changes. This total volume, let's give maybe a blue color. I don't have as many cool colors on this app as I do in Notability. The total volume is just going to be the original volume, 1.5 liters, plus this 0.025 liters. So total volume is just 1.525 liters. And it's the same for both of them. Okay, so when you subtract that, or when you calculate that all out, you're going to get a couple of numbers, which I will pause and calculate. Okay, hopefully I did that math right. I got the 0.2 molar and the 0.243 molar. So notice those are our equilibrium concentrations of HF, so our weak acid, and our salt. And we can just plug those directly in to our Henderson-Hasselbalch equation. I'm going to take a second to write that out. So it looks like this, and you just have to keep track of what goes where. So your salt is going to go on top, and your weak acid is going to go on bottom, and your pKa, your Ka value has not changed from what it was initially, so it's still that number. So I'm going to throw these in and calculate a value. Okay, so when I calculate all that out, I get 3.25. So notice that it's really important to give 2 decimal places, because if you didn't, then your answer would be the same as your answer from part 1, so around 3.3. So definitely give 2 decimal places. And notice the pH went down just a little bit as we predicted. Okay, for part 2 of this, let me at least get you started on it. Okay, so for part 2, we're still working with our original rice table. We are pretending like part B never happened. And we want to know what the pH is after adding a little bit of 0.2 molar potassium hydroxide. Potassium hydroxide is a strong base, and so we would expect the pH of this to be greater than the 3.26 that we found originally. So we are predicting an increase in pH, so greater than 3.26. And again, I think it's always very useful to make a prediction before you do the problem to make sure that you end up with something that's reasonable at the end. Okay, so I wrote back in the values of the number of moles of HF and F minus that you get just from multiplying their molarities times their initial volumes, just like we did in the first step. And now let's look at what happens when you add some potassium hydroxide to this system. So now we're at, oops, I need to change my settings back. So we're adding KOH to the system. KOH is a strong base and will immediately dissociate into K plus and OH minus. K plus is just a spectator ion. It's not going to react with water or anything for that matter. OH minus is a strong base, and I want you to take a look at the species that are present over here from our initial equilibrium. So OH minus has a negative charge on it, so it's going to preferentially react with either something that's positive or something that has an extra hydrogen on it. So H3O plus is a much stronger acid than HF. HF is just weak, but there is such a tiny amount of H3O plus present so that the OH just kind of sees it and is like, oh, that does me no good. And so he actually comes over and is going to steal this hydrogen. So let's actually write this kind of secondary reaction that's happening up above. Let's put it in parentheses like we've been doing. So side reaction, we've got OH minus plus HF, and since this is a strong base plus a weak acid, it's going to react completely to pull that proton off of the HF. So you're going to end up with water plus some F minus. So look at that. So you're actually going to, oops, let's grab my highlighter tool. You are going to react away however much OH minus you added from the HF. And you're going to add, or you're going to produce some excess F minus, and it's going to be equal to the number of moles of OH minus that you had. Let me write that down. So his number of moles will make the HF decrease by that number of moles, and it'll make the F minus increase by the same number of moles. So we just need to determine the number of moles of OH minus, which honestly, if I'm being honest with myself, like should probably be in yellow. So let's do that. Okay, so moles of OH minus equals its molarity times its volume, so 0.025 times 0.2, which should be 0.005, okay? All right, so this 0.005, we said HF was going to decrease by that amount, which notice, this is the opposite of what it was in part B, right? Because we had a plus sign there in part B, and then F minus is going to increase by that same amount. And then from here on out, the problem is exactly the same as the previous part. You just have to like throw in the numbers and go from there. Okay, so you're gonna add together the I and the C rows to find your equilibrium concentrations for both of these. And then you're gonna need to divide by the total volume once you get those number of moles. Same thing over here. And then you're gonna take both of those concentrations and plug them in to the Henderson-Hasselbalch equation. Which I clearly can't actually write, equals the pKa plus the log concentration A minus divided by the concentration of HA. So to summarize, for all buffer problems, you can always use the Henderson-Hasselbalch equation. You can't use it anytime else, but you can use it for buffers. And to use the Henderson-Hasselbalch equation, you have to be able to find these equilibrium concentrations of A minus and HA. Once you have found those, then it's just a matter of plugging those in. So these are equilibrium concentrations, just like they were for K expressions. Okay, so then that's all for this video, but I want to encourage you to go ahead and try the next problem on your own and let me know if you have issues with it.